Alright, now let's see what happens when we try to define the differential length of cylindrical system. This is a little tricky as there is an angle involved right now, unlike the case in Cartesian system. In case of the Cartesian system, we found the differential displacement vector is given by this expression over here. If you look closely, then you'll notice that dx, dy, and dz are all having the unit of distance. Dx means the change in x coordinate, dy means the change of y coordinate, and dz means the change of z coordinate. So basically, all of these terms have the same unit, and that is meter in SI. Right, so these three have the unit of length. In cylindrical system, the three variables that we were using before were r, phi, and z. So we got dx from x, dy from y, and dz from z. So similarly, in cylindrical system, we'll be having dr from r, d phi from phi, and dz from z. That's pretty comprehensible, except there's one problem. dr has the unit of length, and so does dz, but d phi has the unit of radian, or since this is an angle, right? Radian of degree, but in SI unit, we will be taking the radian one. Since phi is an angle, unlike dr/dz, this doesn't have the unit of length. Let me explain what I mean. Okay, let's say there is a center point over here and we're drawing two concentric circular arcs, all right? So these two arcs over here have different lengths, okay? So let's say if this arc length is S1 and this arc length is S2, then obviously it's clear from this picture S2 is greater than S1, right? But the angle they are creating at the center is the same. Let's say this is theta. So what causes the value of S change? It's the radius, right? Let's say this arc is a part of a circle that has R1 as its radius, whereas S2 is a part of a circle that has R2 as its radius. And we all learned a formula a long time ago, and that was S equals to R theta, right? If theta remains the same, the value of the arc length depends entirely on the radius. So the higher the radius is, the higher the arc length will be. If you just say some guy standing over here has covered an angle of 30 degrees in a anti-clockwise direction, it doesn't really convey the exact message about how much distance he has covered, because he could be in this position and he could be in this position, or he could be here also, and depending on where he's starting his journey from, the arc length or the distance he will be traversing will be different, even though in each cases he is traversing this exact same angle. The arc length will be different. Okay, so this is something that we will have to uh, take into consideration. So let's say the arc length of any arc is given by this equation over here, okay, where this is the arc length covered, and this is the angle the arc holds at the center, and this is the radius of the arc. Okay, so what is the differential form of this formula? Well, if we divide this arc into infinitesimally small portions again, each of the portions given by dl, then dl will be r d phi, right? Where r is a constant that denotes the radius of the arc. All right. As the phi changes, the corresponding arc length that is covered is changing, and the whole thing depends on the radius that we're on. All right. So when we're dealing with cylindrical system, we simply do not write a phi d phi. Rather, we multiply d phi with the radius and get the actual distance covered, not the angle covered, to use over here. So basically, in case of cylindrical system, the formula of dl should be ar dr a phi dl, not d phi, and a z dz. I hope it's clear to you why we didn't use dphi. Instead, we use dl over here, because dphi does not have the unit of length, but when we multiply it with the radius, then we get the arc length, which has the SI unit of meter. So this is the distance covered that we'll be needing. All right. So if we convert, so we can write it as r d phi as well. Okay, this will be the representation of dl vector in cylindrical system. Okay, now let me explain what really happens when you try to get from one point to the another and try to denote this change in terms of cylindrical coordinates. All right, so let's say this is a little cutout from the entire cylinder that we would be getting from the r, phi, and z coordinates. All right, so this is an infinitesimally small cylindrical cutout, and let's say we want to get to point A starting from point R. So the r a vector would be the dl vector that we are trying to get. So this will be the RA vector. Okay. Okay, let's say you're standing over here, then you set out your journey and move a distance equal to dr along the direction AR, right? This is the direction of AR. Okay, after getting to the point Q, you go to the B point along this direction, okay? This is the direction of a phi. Okay, basically the Apqp surface is part of the circular surface of the cylinder. Okay, so when you are moving from Q point to the B point, you are moving along the circular surface of the cylinder, and the circular surface of the cylinder is basically the direction of a phi. So the distance you covered is given by QB. Okay, so if I write QB equals to d phi, will that be right? No, because QB is a length, but d phi is an angle. All right, as we know that dl, the change of arc length covered, equals to the radius times the angle covered. So we have to multiply d phi with the radius of it. Okay, we will get r d phi as the length covered along the QB direction. So now you're at the B point, right? So let's just move along the z-axis towards the A point to finish off your journey, right? So you're moving a distance equal to dr along the AR direction, then you're moving a distance equal to r d phi. R d phi is length itself. You're moving along an arc length equal to r d phi along the A phi direction to reach to the B point, and then you move a distance equal to dz along the az direction. Okay, so these three components will give you the final dl. That means the ra vector that you are trying to achieve over here. All right. We have found the differential length formula of cylindrical system, and now it's time to move on to the differential area calculation. As was in the case of Cartesian system, there will be three major surfaces that we'll be talking about here. First of all, let's talk about the Apqp surface. Okay, so this is the surface I'm talking about, the circular surface of the cylinder. So Apqb is a tiny part of the circular surface of the cylinder. All right, so the area of this tiny part is given by the dimensions multiplied. All right, so AB is equal to DZ. Okay, and QB, as we've shown earlier, is equal to RD phi. So if you look from this direction, you'll see it as a rectangle that has a width of dz and a length of rd phi. So ds will be given by rd phi. And just as before, if we want to turn it into a vector quantity, then we'll have to find the vector that is perpendicular to this surface, and the vector that is perpendicular to this surface is the radial vector. All right, so AR will be the vector perpendicular to this cylinder surface, circular surface of the cylinder. So AR will be the vector perpendicular to it, so we denote it as DSR. And if you look at the ASRQP surface, then we'll see this is the surface I'm talking about right now. So if you take it out, ASRQP, it has a length of dr and a height PQ of dz. So the area will be dr dz, and the unit vector that is perpendicular to it will be a phi. Okay, so ds phi is equal to dr dz, a phi. Okay, and finally, if we talk about the top surface over here, it's kind of like curved. So if we take ASDAP surface, the area will be RD phi multiplied by dr. Okay, or we can write it as RD phi. And if we turn it into the vector, then the perpendicular vector to the surface will be AZ. So AZ, if we put it over here, it turns it into DSZ and a bar. And finally, if we want to calculate the differential volume from these differential quantities, you can approximate it as a little rectangular parallel pipe that has three sides, namely dr, rd phi, and dz. So multiplying those three, you will get the differential volume that has this value of rd phi, dr, dz. All right, and of course this is a scalar again.